Title of his talk is Technology Challenge on the Road to Designing and Building the SKA. Professor Jajwant Gupta.
सर आगे चले जाइए next.
Yeah, that's fine. Yeah. Okay, a very good afternoon to all of you. What I will be doing is to follow up on what Professor Robert Brown has told you, an excellent expose on what the SKA will be like, to actually highlight what are the technological challenges as one moves towards completing the design and starting the construction of this mammoth project, and with the hope to highlight what are the exciting things that both we as scientists and colleagues from industry can work together with us to achieve. And so this is just an overview slide. I'm just trying to see if there's anything here which Robert did not cover. I don't think so. So I can just move on very quickly, except just to remind you again that the full SKA will be 30 to 50 times more powerful than the best facilities that we have today. And you can see how the radio astronomy facilities over the years have grown. It's like our own Moore's law, so to speak. In terms of the design and technologies that are involved, it's important to understand that, because that is what then leads us to what are the challenges. And again, a lot of this Robert covered, that you have receptor stations spread out over large distances, up to 3,000 kilometers in the full SKA, in addition to the central compact core that he showed in more detail. More importantly, again, as we saw, that in order to cover the vast frequency range that the SKA is aiming for, you need multiple detector technologies. You can't just have dishes. The dishes will be used only for the higher frequency part, and for the very low frequency part, as you saw in the previous talk, we will be having dipole based antennas, which is again a different technology, again with its own set of challenges. And in addition to that, as you already saw, that the total data volume that has to be transported from these faraway antennas to a central location is quite tremendous. And it is also requires state of the art low noise electronics, because finally when you build such an instrument, to extract the maximum sensitivity, you want to reduce the unwanted contributions from the receiver noise and the receiver electronics. So you make that extra effort to design the best possible electronics, and then it is to be backed up with the real time capability to process all these signals, and I'll explain a bit more of these in detail as we go along. And then finally, in order to make the image that the astronomer wants from the observation, you actually have to further work with the data, and that requires supercomputing capabilities, which again we'll look at in more detail in a moment. And finally, in order to make this all work as a coordinated observatory running across 2 continents with the headquarters in a 3rd continent, you need a fairly complicated and sophisticated telescope management structure, which is both algorithms, software, and the way you build up the model for how people and machines interact with each other. And so all of these then lead to some of the main technological challenges, and I'll go through them in a bit of detail, starting with antennas and electronics, and bunching this whole set together in what I call the general data challenge, and then the observatory wide management system, managing the power requirements, and then the challenges of producing these things in large volume at the quality that is required to make an observatory that lasts for several decades. And to convert those challenges into numbers, I have this table here which says what you need as key items for the SKA. So for the mid frequency for SKA phase 1 and for the full SKA, and again you can see in terms of the requirements, when you go to full SKA, these are really very challenging, but even for SKA phase 1, there are some of these requirements which are quite challenging in terms of signal transport, signal processing, and the software required, the data storage, as well as the power required to run the observatory. And so, let us look at some of these in more detail. The antennas and electronics come with their own set of challenges. As you saw, the antenna for mid frequency, it is relatively traditional radio astronomy antenna, but it has its own specific requirements in terms of the accuracies that have to be maintained, and finally you have to produce a fairly large number of them, at least of the order of 130 in the beginning and many more for the full SKA. The SKA low antenna, which are these dipoles, they come with their own challenges in the sense that it is supposed to work in a full 300 megahertz of bandwidth, and you have to design this very well so that you get the right kind of pattern from the antenna which works equally well over the entire range of frequency. For the mid, it is not possible to cover the entire range of frequencies with a single receiver attached to the antenna. So, it is split into multiple receiver systems, all of which can be located at the final focus and rotated and brought into place depending on the frequency of observation. And these again are not very easy to design. As you can see, the bandwidths over which they work are of the order of a gigahertz, which is a very large bandwidth. And in addition, for these the mid frequencies, you definitely need to cryogenically cool the receivers so that the physical temperature is low enough to minimize the unwanted receiver noise. And so that itself adds additional challenge. So, here is what has happened so far as part of the design work. There are designs now available for these feeds and receiver systems for all these bands, most of these bands of the SKA. The ones in bold are the ones being highlighted and targeted in the early phase. And but there are still challenges in terms of how will you manufacture them to the right level of detail and accuracy, and again there is significant potential for some of that happening in our own country. Similarly, the SKA low antenna looks simple. It just looks like a wire frame, but it has to be done well so that it survives well in the harsh conditions in the desert, where if you have only 100 people, then there are not many available to go fix it, and so it better be robust. And I'll come to that point a bit later on. Moving from there, I've clubbed all of these in one generic feature as the SKA data challenge, and some of this again Robert alluded to when he showed this. But basically, if you look at the flow of the signals through the observatory from the time where the voltage is picked up by the antennas, it goes through transported to the central signal processor, and then you take the result from there and you run it through the science data processor, which gives you the final images and the products that the astronomer can use. But there is still a challenge to get those products to the astronomer, because even at this point the rate or volume of data can be quite challenging. And so, let us look at that a bit more in detail. So, this is the same picture that you saw a short while ago, and again just to emphasize that the 2 petabytes per second is a humongous rate in terms of being able to handle this in a robust and reliable manner. And though it is converted down to terabytes per second is also not trivial. And when you do the real time signal processing, it is something which is of the order of several tens of petaflops, if not more. And when you do that, you would hope that the data volume comes down, but not too much. It is still of the order of terabytes per second, and this then you need to put through the science data processor, which is a much larger computing challenge, the order of 130 petaflops or so. And finally, when you do that, it still produces data which is of the order of 300 petabytes per year, as Robert was showing. And all of this poses a significant challenge in the overall handling and processing, and there is a lot of work that has gone on to design these systems optimally. It's still it remains for us to build them and show that they work well in the conditions. And here there is a lot of potential for FPGA based processing, some amount of GPU based processing, and this is basically equivalent of a supercomputer that you need over there in order to do the data analysis. And so this again we saw a short while ago that the total data archive just for SKA phase 1 is a staggeringly large number. And once again, this needs to come to the users sitting in different places, including India and other countries. And the plan is to have these SKA regional centers where the original basic data product coming out from the 2 locations of the observatory will be distributed, and from there it's farmed out to the end user, and end user can add additional value-adding pipelines to get to the specific science goals that they have in mind. And it's our plan to have a regional center in India for the benefit of our astronomers. This again, you saw a similar diagram. The challenge here is to get this large volume of data across the globe, and there's plans being drawn up, pilot experiments being done to see how well does this work in transferring large volumes of data in a sustained and reliable manner, and can we have dedicated SKA primary pathways for taking the data out from the 2 observatories to other locations. So moving from there to the observatory-wide management system. So as I said, in order to run this, it is like running a big complicated factory or a plant, and you need a system that can handle this vast distributed set of receptors and the whole end-to-end process from the time where an astronomer thinks of a project and a proposal to be put in, from to there to scheduling the observations, to making sure everything runs fine, coordinating with each and every part of the observatory, ensuring that the final data product is delivered to the user. And so that is in some sense like the brain and nervous system of the entire observatory, and it's a major piece of work in both terms of algorithms and software and man-machine interactions. And this is one of the areas where India has led the work in the design phase, which we worked along with partners from Indian industry as well as with partners from other SKA member countries to do the work for the design of the telescope manager. It took 4 years of work. It was finished in the middle of last year with the successful completion of the critical design review, and we are looking to be able to contribute significantly to the construction of this system as we head to the construction phase. And we'll hear a bit more about it later in the afternoon. Moving from there, as you can imagine, this whole observatory requires megawatts of power, and it's of the order of 5 to 10 megawatts for SK phase 1, going up to 50 megawatts for the full SK. So it's like having a small power plant that you need. And this again is what Robert showed, the first attempt by the community to do that. So this is a 1.6 megawatt power plant in Western Australia, built to power the existing facilities there and to act as a pathfinder to show whether this can be done. So besides, then I come to the last part, which is the fact that all of this has to be done in fairly large volumes at industry scale, whether it is antennas or it is the electronics or it is the supercomputing capability. And when it comes to that, it has to be done in a manner which emphasizes the reliability of what is being built, because it's going to be put out there in the desert, most of it, and so it should have a very high availability, very low failure rate. It should survive the harsh environments. And so this is one area where we think that industry participation would be very essential, because there would be the way of doing things which is much more robust and can withstand and can have a much larger mean time between failure and a lower maintenance, which really is essential for this project, the way it's designed and the way it's located. And so this then brings me back to my summary, and I leave you here with again the main facts which highlight the challenges. And again, just to reiterate that in many of these there is a significant opportunity for industry participation and contribution, and I think the rest of the rest of the talks and the discussion session, I hope, will bring out this aspect. So good. So I've saved a couple of minutes for you in the program. All right.